Okay, thanks.
Okay, good. Boris Glavic, still in Illinois, but I think you soon also at UIC.
Starting January. Hey, so I'm going to talk about using semirings for an application in incomplete databases, and specifically to approximate certain and possible answers beyond sets. So we all know here in the room what an incomplete database is, and we all, I think, agree that these are principal techniques for managing uncertain data. And of course, the complexity landscape is relatively well understood, right? There's many important results. Many people here in the room have proven them. And so I'm not going to go through all of them, but still the fact remains that even this is intractable even for relatively simple queries, depending on the representation system that you use. Okay, an incomplete database is just a set of instances. Deterministic database is called possible words. Like, for example, here we have 3 possible words where we are uncertain about the location of certain people, and some people don't exist in every word. Okay, so then this gives us a very easy way to define query semantics. It's basically just we evaluate the query in every possible word. That's just deterministic evaluation. So this can be applied not just to queries, but any kind of computation you can come up with. As long as you have a deterministic semantics, you can lift it to a possible word semantics. And this gives you then all of the possible query results you could get independent of the uncertainty. Okay, other types of information we can extract here is we want to maybe reason about which rows could possibly in the result. That's essentially the possible tuples of a database. That is, there exists at least one word where this tuple is in this word. Yes, typically people define it with respect to queries, but here for me it will be useful to define it over databases. And then the certain tuples in the database are all of the tuples that exist in every word, right? And then I can redefine certain answers and possible answers by just applying it to the result, applying possible word semantics and then throwing this certain and possible operator at it. Okay, that's not practical, but let's ignore this for a second. Cool. Good. So what I want is basically a holy grail. I want some practical model for uncertain data management. I want to support BACS, right? We want to support regular relational databases, and maybe perhaps even more than BACS. I want PTIME data complexity, and this will only be achievable through approximations, since we all know that this intractability results. And I want to support complex queries. So what do I mean by this concretely? I want full relational algebra with aggregation, sort-based operations, and perhaps also recursion. So I want basically something that seems impossible, right? I want it to also be modular. So I want a query semantics that's closed under queries. Everybody working on certain answers knows that this is typically not the case, right? Certain answers are not closed. We cannot take the certain answers of a query and evaluate a query over it and get certain answers for that query. I want it to be compact. I want to be able to flexibly trade the size for approximation accuracy. So we want some mechanism to compact things at the loss of accuracy. And I want it to be compatible with many existing uncertain data models and data cleaning paradigms. So what I mean by that is I want to be able to approximate these paradigms and then afterwards operate in my world and run queries in my model. Okay, so how do I achieve it? It's basically trivial, as you will see. Everybody in the room will immediately see once I show you why this works. So let's first start with generalizing incomplete databases. Let's just say we want incomplete database beyond sets, and we are all seen like all of the semirings that exist that we can use to express things more than sets, natural numbers for BACS, provenance, semirings. We saw many variants today and yesterday. Temporal databases, by the way, can also be modeled as semirings, access control, and so on. So we want all of this as incomplete versions. So how do we do that? Well, I don't have to stay on this slide for too long. I think everybody in this room knows what the semiring is. It's a set with binary operations that have neutral elements and fulfill a bunch of equivalence laws like both operations. I'm looking at commutative semirings for the formal languages people, and have neutral elements and there's distributivity. Okay, and then we can apply this to define relations. The idea is basically if we have some tuples, an n-ary relation over some domain U is then just a function from the tuples to an annotation. And with finite support, that means we only allow finitely many elements to have a non-zero annotation, which basically means we are using 0 to say the tuple doesn't exist. And then we directly have a finite representation system where we just ignore, we don't explicitly list the tuples that we're mapping to 0. Okay, good. Natural order, also I don't have to, we saw this many, many times, and we are basically relying on natural order to make all of this work. So in a semiring, right, K1 smaller K2, if we can find some K3 that we can add to K1 to get K2. And if semiring, this natural order is a partial order and it builds a lattice structure over the elements of the semiring, then it's an L semiring. I think Peter Buneman had like a paper where this terminology was used. So basically, the idea is then we have our greatest lower bound and least upper bound operation for any two elements in the semiring. And right, so for example, if we take the natural number semiring, back semantics, if we have like K1 is smaller than K2, it's just the normal order you would expect in natural numbers. And then the greatest lower bound is min and the least upper bound happens to be max. But many other important semirings also have this kind of lattice structure to them. Okay, so now let me lift incomplete databases to K relations. That's trivial. It's still a set of instances, just that every instance happens to be a K relation rather than a set table, a set database. So possible word semantics works out of the box because we have a deterministic query evaluation semantics for semirings. We can just apply it here too, right? So that works. But what about certain and possible answers? That's not so clear, right? So now what I'm claiming is that we're going to define now certain annotations, because now a tuple may exist in different words, but with a different annotation. So now we have to figure out what's kind of like and this is where then the ordering and this least upper bound and lowest greatest lower bound come in. So so the idea is basically the certain answer, the certain tuples or certain annotation of a tuple T in an incomplete database D is now just going to be the least upper bound, so the greatest lower bound of all of the annotations of the tuple across all of the different words. And for possible annotations, the opposite, we're just using the least upper bound, again, across all of the possible words. So this coincides, I mean, the first sanity check is, of course, this should give us the same thing for sets and backs as we are used to, and it does, right? So for backs, maybe it's not so common what it is, but for example, Lipkin had some work on this. For backs is basically the smallest multiplicities that makes sense. If a tuple appears twice in this word and 3 times in that word, we say it certainly at least exists twice in every word, right? Okay, cool. Good, so far so good. Let's apply this to some example. Here I have an incomplete back database with 2 possible words. I can now reason about the possible and certain annotation. For example, Peter US, the certain annotation is 2, since Peter exists at least 2 times in every possible word. The possible annotation is 3. Peter does not exist more than 3 times in any word. And for Boris, the certain annotation is 0. I was using this convention to not list tuples that have 0 annotation in the tables explicitly. Okay, great. So now we have a way to do certain and possible answers over arbitrary K semiring K relations, as long as for the K semiring K has this lattice structure to it. Okay, good. Any questions so far? Right, that's kind of like trivial for everybody here in the room, I hope. So good. Now, what I'm now claiming is, now let's approximate the sufficiency, right? I wanted this PTIME data complexity that otherwise we can't get without approximations. Okay, good. So how does it work now? Let me first define like a containment where I'm lifting the natural order now to databases. I'm basically saying a database is contained in another database with respect to semiring K, so it's a K database. If for every tuple, the annotation in one database is smaller equals than the annotation in another database. And again, that generalizes what you would expect from containment in sets and backs, right? So that means now I can define an under-approximation based on that. I'm just saying some K database D, so not an incomplete one, just a deterministic one, is now just a database which is containing the certain answers. It's containing the certain answers is a superset, so to say, of this database. And I can also do this with over-approximating possible, just the other way around. I want some database where the annotations are always a larger equals than the annotations that the possible tuples would get of this incomplete database. Okay, good. So this is like definition so far, right? But let's see, how can we compute this? Well, and this is completely, before we get how to compute it, just to show that we can take existing representations of uncertainty and map it into this world. So let's say, for example, a very common thing that everybody here working on probabilistic databases would know, tuple independent database. I'm now using the incomplete version of this, we can model it as a set of certain tuples and a set of possible tuples. And then the models, that means the possible worlds encoded by this tuple-independent database, is then everything in between. That it contains at least the certain tuples and is a subset of the possible tuples. Okay, good. This immediately gives me a very easy under-approximation. The certain tuples is an under-approximation. In fact, in this case, precisely the certain tuples. And the over-approximation is just the thing itself. That's exactly the possible tuples in this case. Okay. Very easy. We can also do this for data cleaning. So for example, let's pick a very simple type of data cleaning where we have a key constraint that is violated on a relation. And let's consider all of the subset repairs. These are the minimal repairs that are minimally different from the original database created, in this case, by deletions. Now, basically, I can I can treat this as an incomplete database where the set of possible words are just going to be all of these repairs. And these are basically all of the databases where none of the keys appears more than once that are contained in this initial relation that violated the key. Okay, so then what's an over-approximation? Well, it's just the thing itself. What's an under-approximation? I can basically pick all of the tuples that don't, where we don't have another tuple with the same key. Not maybe a great under-approximation, but just to illustrate that it's very easy to get from common types of uncertainty, whether it be incomplete or probabilistic database models or some kind of data repair where people typically do heuristics. Now we can kind of model all the possible words. Yes?
Did this use any of your algebraic structure, this slide, or is this just...
No, I mean, it's basically, it's a B relation here. I'm looking at sets. I could define it for backs too, right? But basically, here the tables are just set tables, right? But they could be back tables that would work too, right? Yeah. So, and in practice, actually, we always work with back tables because we implement this in actual databases. Okay, cool. Now, good. So now I'm going to define some new data model that is just trivial because it just takes like the under-approximation of certain and the over-approximation of possible and just makes this one annotation. It's just for convenience. You could also just, as we will see, we can basically treat this independently for most part of the talk. But basically what we are now doing is each tuple is now going to have a pair of annotations from a L semiring K, such that the first element is always going to be smaller equals than the last second element. The purpose of this will be the first dimension will be an under-approximation of possible certain, and the second dimension will be the over-approximation of certain possible. Okay, so this is basically a semiring. I can show this quite easily. There is this concept of a product semiring where we just take two semirings, pairs of elements from them. Also, this point-wise definition of addition and multiplication is also a semiring. So great. But to prove that what I have here is a semiring, I just have to show that addition and multiplication stays within this subset of k squared. And this is easy because addition and multiplication in semirings preserves the ordering. So that means this is also a semiring. Good. I'm going to use this notation like the downwards arrow to access the first element of such a tuple and the upwards arrow for the second element. Okay, now I can lift this to databases where I just apply it basically to each tuple. So I'm just projecting on the first annotation value or the second annotation value of this 6. Okay, good. So this is for any natural ordered semiring, this is actually also a semiring. Again, based on the concept that product semirings are semirings with point-bias addition and multiplication. Addition and multiplication preserves natural order. So this ordering between the elements will always preserve. So this is like a substructure of the k-squared semiring. Good. Now I can define what it means for such an uncertainty annotated database or UADB to bound an incomplete k database. It's basically if the first dimension under-approximates certain annotations and the second dimension over-approximates possible annotations. Okay, good. Now, here's a trivial but great result. I have already a bound-preserving query evaluation semantics. Sorry, I'm jumping too fast. Now I want, of course, operations. I want to be able to run queries on this stuff, computations. And I want this to be bound-preserving. So what I mean by that is if I have an UADB that bounds an incomplete database, I want that for any query from the class of queries, the query result also bounds all of the possible query results. Basically, computations preserve this bounding. That's why I call this bound-preserving query semantics. Okay, good. Now I show you one that is totally trivial and just works naturally, proves itself. So for any positive relational algebra query, the standard k-relational query semantics is bound preserving. So why is that the case? Well, in any naturally ordered semiring, the addition and multiplication operations are monotone with respect to the natural order. So that means if I start with something that is smaller than the certain answers, I run a query over it, I get something that is smaller than the certain answers of the query result. And the same for possible, the symmetric case for possible. So this is super trivial. I mean, I can write down the proof, and I'm not a theoretician, right? The proof is basically, for addition, it's very easy to see because natural order is defined based on addition. For multiplication, you just use distributivity, reorder the terms, and you have it. Great. So I basically get a bound preserving query semantics for free, totally for free, just based on standard results. Yes.
That works for self-joins.
Sure, it's just right. It's just based on the self-joins use multiplication. It works for multiplication. So yes. Right, it's kind of surprising maybe, right? But if you think about it, it's totally trivial and natural, right? Okay, good. This works for any positive relational algebra query, as long as your semiring has this lattice structure. Otherwise, anyway, certain answers and possible answers in my world are not defined. Okay, now, more interestingly, perhaps, if we use a mono-semiring definition of the difference operator, then if you apply it pointwise, it's not bound preserving. If you think about it, it makes sense, right? If we start with an under-approximation, this is not monotone. So, but what we can do is we can define a semantics that works. And how this works is basically the lower bound of a tuples annotation in R minus S is going to be the lower bound of the annotation in R minus applying the monos, the upper bound on the annotation in S. And for the upper bound, it's opposite. Basically, we make the worst case assumption for R and the most best case assumption for S. So we subtract the largest possible element in S from the smallest possible element in R, and this gives you then again bounds. Okay, good. So maybe also surprisingly, now we also get a recursive data log, a positive data log for AU-DBs is bound preserving. We again get this for free, right? We are just calculating computations in a single K relation. So dense results here from last year gives us actually some convergence bound. So if a semiring, and this results basically use the length of chains in with respect to the natural order to provide some query-specific bounds on the worst-case bounds on the convergence of data log. And basically, because in our case, the two dimensions, we treat them completely independently. If we have a certain bound n for a query over a K relation, now we get the same bound n for convergence of these approximations that we have. Also completely for free, right? Nice. Good. Okay, cool. So how does it relate to all existing works, right? I mean, completely for free, I have to say that, right, so where do we pay? There must be something where we pay, right? And I have to admit that we pay in terms of accuracy often, right? Because we basically map directly into our model, we approximate early, and then you miss some opportunities where in a system that knows the full query and the data, you could preserve some more correlations, for example, that you could use to compute more precise bounds, right? Okay, good. But basically, the nice result is also because we are closed. If I take, let's say, somebody's favorite consistent query answering algorithm for a particular type of constraints and particular class of queries, if we have a query that is not supported by that, but it has a subquery that is supported by this other approach, we just use this other approach to evaluate the query, the subquery which is supported, then map this into our world, and then continue in our world. So that means we can kind of utilize all existing techniques that are out there. We can kind of bring them into the fold. And this is also applicable, again, this happens because we define this closed semantics and this way to map from existing incompleteness representations into our world. Okay, good. Cool. So that's nice, right? But now if we want to go beyond full relational algebra, if we want to also look at aggregations and maybe also for certain types of incompleteness, they are not really efficiently representable in a model where you have concrete attribute values. So what I mean, let me give you a few examples, right? One common problem is that for operations like aggregation, certain answers are typically empty because this operation will return a different aggregation function result in most words, right? So that means certain answers can be defined, but are maybe not super useful. Also, certain types of uncertainty cannot really be expressed by just having concrete values in tuples, right? So, for example, I cannot express something effectively. A person exists, but their salary is between 100 and 200,000. I could express this as 100,000 tuples with all of the possible salary values that are all uncertain, but that's not a very effective way to represent things, right? And then also, like operations like sum aggregation may produce exponentially many results, right? This is all of the sums you can get from a subset of a set of numbers, right? That can be exponentially many. So there's existing work on that, of course, right? We're not starting from nothing, right? For example, I would say this is related to some degree to representation systems that use labeled nulls. For example, C tables, M tables, and others. Also, this is also related to let me call them factorized representations like block-independent databases and so on. And also related to a lot of extensions of certain answers to queries with aggregation, where also some people in the audience have worked on that, where instead of returning empty certain answers, you return the smallest possible aggregation value and the largest possible aggregation value. This is nice. However, the problem with that is now we have not a closed system anymore. I cannot take this aggregation result and join it with something else, for example. And also, this is related to a technique from programming languages. Let me just mention this, called abstract interpretation, where you do sound over approximations of fixed point computations. Anyhow, so what we're going to do is we're going to take this idea of intervals, but we're going to make them a fundamental part of our data model. So for any domain that has some order, we can define that should be total order here. We can define some interval domain where we just have like a lower bound and an upper bound, and this interval is essentially representing all of the values that fall between these bounds. And then we want operations to be defined on this domain in an over-approximating way, so that if we start with two intervals, as a result, for example, of adding them together, should over-approximate all of the possible sums that you could get if you pick a value within the left interval and a value in the right interval. And you can actually prove this. We did this for a bunch of arithmetic operations, comparison operators. Like here, for example, any monotone operation with respect to the ordering, you can just do it pointwise. Other operations, you have to be a little bit smarter. Multiplication, you have to be a little bit smarter, since this is not necessarily monotone. But here, for example, is also equality comparison. When is it guaranteed to be equals? If all of the four values are equals. When could it be equals? If the intervals overlap, then I can pick one value that would match. Okay, now we're defining relations on that. We take the same ring as before, just under-approximation of certain and over-approximation of possible. But now we make our values intervals. So that means the annotation domain doesn't change. We just change what our values are. Okay, good. So then such a AU-DB, or attribute uncertain database, is then encoding also a set of possible words that we can get by basically distributing the annotation mass of tuples to concrete tuples that are bounded by the intervals of the tuple. Okay. That's a mouthful. Let me show you a concrete example. Here we have, like, for example, two people. And I'm showing you two possible words here. For example, the first word I'm getting by deciding that there's one instance of this tuple Boris with the salary within this bounds. And the second, Peters, I get by choosing 3 Peters in total. And each of these Peters have to have a value between 140K and 400K. Okay, good. So you can see that this can be used to compactly over-approximate large number of tuples, which is what I need for aggregation, and also the things like a person has an uncertain salary within a range. Okay, good. So now I can define also this bounding again. I can define it also just based on the incompleteness itself. I can also just treat this as a useless incomplete data model because it's not closed under most operations. Thanks. But I can still say, like, it over-approximates a set of possible words of an incomplete database. Like here, the one below over-approximates this incomplete back database on top because I can because it has these two possible words and several others. Okay. Now, good. An alternative interpretation is basically that the lower bound of the annotation still under-approximates certain tuples, but now with attribute level uncertainty. So, for example, this statement, the second tuple is a statement that in every possible word, there's at least 2 Peters with the salary within this range. Right? So the range might not be tight, and that's also how we get efficiency in the end. Okay, cool. Good. Now, so queries over semiring relations, I don't want to go over this again here necessarily in this environment here, where people already know this. But we can define the standard relational algebra in terms of semiring annotations, where union and projection are based on addition, and join is multiplication, and selection is multiplying with an indicator function. If the tuple fulfills the condition, then it's the one element of the semiring, doesn't change the annotation. Otherwise, the zero ring element of the semiring, we are deleting the tuple from the output. Okay, good. So the nice thing is this all works over this extended thing too, because we just have different types of domain values. Nothing new is required except for selections, right? Because selections look at the values of tuples. So now what we need is basically we need to now take our over-approximating semantics for this arithmetic and comparison and logical operators and apply this and map this back to the semiring. So what we do is, for example, if I compare this interval 1, 3 to 3, 3, I get an interval false true, which means the result could be false, but it could also be true. So it's a result, and so then basically then how do we map this back to this k-relational semantics? We just map false to 0 and true to 1 as before, but now we do it in each dimension. And this turns out to work out. Okay, good. Now aggregations, which was one of the main motivation for us to do this kind of stuff. So basically, there is an existing representation system for Mr. Valtan and other people for aggregation results. But basically, this relies on a semi module where we are combining semiring elements with the monoid domain, which represents our aggregation function. Turns out this our interval versions of these monoids are also monoids. However, it turns out that you cannot have a semi-module that is bound preserving. That would basically, I'm not sure whether it exists in the semiring, but if it would exist, it would be not, it would violate, would not be bound preserving. Okay, good. What do? We escape into uncertainty. We basically define another kind of semi-module style operation that is just using the multiplication in our interval domain, which we already showed to be over-approximating. And so this part here is now, for now, only in natural numbers. But I think it could also potentially be extended to other semirings if you can under-approximate this stuff too. And then we can do this. We have to reason about which tuples have the same group by values. The group by values can also now be uncertain because we want to also do aggregations on top of aggregations. And so then we basically have to reason about which tuples could belong to a group, what's their lowest and largest multiplicities, and what's their smallest and largest values. And that can give us like a sound bound on the lowest and largest possible aggregation value. We also extended this to sorting-based operations, where we use the fact that we have this uncertainty of values to represent uncertainty in the sort order, and also can do windowed aggregations over the stuff. That's our latest work, published this year. Good, let me conclude since I'm running out of time. I present to you this AU-DB model, which is a lightweight but pretty powerful uncertain data model, which can under-approximate certain answers and over-approximate possible answers, possibly with attribute level uncertainty. And I think the fundamental idea here is, apart from exploiting semiring stuff, is this idea of taking this idea of ranges but making them first-class citizen in the data model. Good. The next thing would be to go to more expressive mechanisms like iterative computations, and right, for also now this interval domain stuff, getting better bounds, because we have essentially tuples are boxes, and so we have no correlations between attribute values and tuples. So going a little, I don't want to go to full constraints, but I want to maybe use more expressive set representations like zonotopes or other types of restricted types of constraints where certain things are still feasible. And then also, like, right now we just have intervals, but you could also think about using an arbitrary partial order, for example, like a taxonomy for data that is not naturally has an order to it. So that we have two implementations. One is GPROM, which is like a compiler that takes like SQL plus uncertainty and compiles it back into SQL for almost any database. And we have a notebook system that supports a simpler type of this data model for cleaning operations and then running queries over this cleaning operations in the notebook. That's called Visio. That's mainly work of my student Sue and my great collaborators Oliver and Aaron from SUNY Buffalo. And so to show you, okay, right, so one more thing I wanted to actually show you also. This is actual TPCH queries on 1 GB database running in our model, right? So we can actually run this. We're comparing this against deterministic, and yes, it's some overhead. This can probably further be reduced with some smart engineering things that we haven't done yet. But we can actually run this on large instances with complex queries that nobody could support before, right? So I just want to mention that here too. And to show you that I'm not lying, here's like a tuple-independent database. This is a GPROM system. I can say I want to do some uncertain query processing. Here I define how to map from an existing uncertain data model into our model. I'm saying just this P is like a probability attribute of a tuple-independent database. And I'm running sum of A group by B. And right, this is running in the background on a Postgres database. If you want to see what happens under the hood, you can see like the relational algebra trees that are being generated as part of this at some point and so on, right? Okay.
Boris, thank you for the talk. So you showed us that these under and over approximations behave well under the relational algebra operation, say, but you didn't tell us about the goodness of the approximation. So do you have a quantitative way to make sense of how good are these approximations?
Right, so we don't have any results of kind of a bounds of how good these approximations are. And that's, I think, kind of like one of the things that we need to work on, right? We have, except for some really trivial results. For example, this also generalizes existing results on certain answers. Like, for example, for databases with nulls, if you treat the nulls as constants, right, and you just evaluate the query regularly, you get an under-approximation. And that kind of translates into our model too, but also that doesn't tell you how good this under-approximation is. So I think that's one of the biggest gaps here, right? So,
suggestion or a vision of what I'm thinking here of the inconsistency tolerance semantics of, for instance, making Bienveni. I don't know how much you've seen of that.
No, but I have to look into
the sequence of improving approximations.
Ah, I see. Yeah.
By looking at fewer repairs, for instance, I mean, or more repairs.
Mm-hmm. Oh, I see. So we basically would start with like maybe something that's a smaller under-approximation that's...
It's still qualitative, it's not quantitative. I was asking if you have any quantitative approaches here.
No, I don't, right? And I think that's kind of the biggest gap there. And we know from practice that if we apply this, we applied this to practical data sets that have data quality issues, and it works quite well. If you apply it, but if you, another thing we try to use it for is like deterministic approximate query processing. You compress your database into a smaller AU-DB, yeah, right? And but that doesn't work well in most cases. And it's not surprising because we lose all of the correlations. So I think it's kind of going to be interesting to see what happens if we go to like zonotopes, for example, to preserve some of the correlations, how well this works. But it would be really interesting to have some kind of, exactly.
Yeah. Along those lines, do Viterbi semirings satisfy your requirements for L semirings and Monas semirings and all that?
Yeah, they have a lattice structure, right? So yeah.
Okay, so can you do probability density functions, for example, for probabilistic reasoning?
I guess so, right? If we can express it in Viterbi semirings, we're good, right? So yeah.
I mean, that could be one direction.
The Viterbi semiring is a semi-lattice, but the meat, the dual operation, is not the multiplication.
Yeah, as long as it exists, right? Yeah.
So